This is going to be a fun video because we're going to finally start talking about geometric algebra in 3 dimensions. What we're going to do is first review what we've been able to set up in G2, the geometric algebra of 2 dimensions, and then we're going to finally set up G3, the geometric algebra of 3 dimensions. We're going to add a few more mathematical objects, and if I've been explaining this stuff clearly, it shouldn't feel like you've actually learned too much in this video. Let me quickly review what we did to set up G2. What we did was start off with some vectors, namely 2 vectors. We had one vector, which I drew as this horizontally directed vector called E1. This is of length 1. And we had another vector orthogonal to it, also of length 1, called E2. So 2 vectors in our basis for G2, E1 and E2. I also called these sorts of objects the vectors grade 1 objects because they're formed by taking one vector at a time. We can go down one rung on the ladder to consider the scalars, which are formed by taking no vectors. And I represent these as just numbers, like 1 or 5 or negative 10. Geometrically, we designate those by points. And again, these are the grade 0 objects. And now we ascend to the highest rung on the ladder to consider the grade 2 objects. And what were these? These were the bivectors. How do we form the bivectors, or how did I motivate the bivectors? We were considering the wedge product between E1 and E2. That is E1 wedge E2, which we later found to be just equal to the geometric product E1 times E2. So let me write that there, E1, E2. And remember what the geometric interpretation of this was. We have E1, then we have E2 there as sides of a parallelogram. Complete the parallelogram, and then we put that circulation symbol in there to denote the orientation of this area element. So this is E1 wedge E2, or E1 E2. And remember what this is. So this is an abstract area element. So this object, this bivector, contains information about the area and the orientation of the area. Using the language of linear algebra, we could say that G2, the geometric algebra of R2, is a 4-dimensional abstract vector space because we have 4 elements in the basis set. We have 1 scalar, 2 vectors, and 1 bivector to make up the 4-dimensional vector space. Now, in addition to defining what the mathematical objects are, we want to do some operations. And the principal operation that we're concerned with in our talk of geometric algebra is the geometric product. And abstractly, this has a lot of nice features, just to remind you what those are. It's associative, so if I have 3 vectors, u, v, and w, uv times w on the right is equal to vw times u on the left. So it's associative. It also obeys the distributive law, so u times the sum of v plus w is equal to uv plus uw. And it has another nice property, which is that if you square any vector, let's say u, you square the vector under the geometric product, that's equal to just u times u. That's equal to a scalar. Which scalar is it? It's the squared length of the vector. So these are some of the nice properties of the geometric product that I just want to remind you of. Besides the geometric product, we had a couple other very useful operations that we could define. We were talking about the dot product quite a bit. Remember what this dot product is? This is an operation that takes in 2 vectors and it outputs a scalar. And we write this as u dot v. So inputs 2 vectors to grade 1 objects and outputs a grade 0 object, so it's grade lowering. And u dot v can also be written as 1/2 uv plus vu. So in terms of the philosophy here, we could think of the geometric product as the principal operation, whereas the dot product is one of the subsidiary operations because it can be defined in terms of the geometric product. Besides the dot product, we also had the wedge product. This is the other pretty useful operation. Now the dot product is grade lowering. The wedge product is grade increasing. So remember, when we take in 2 vectors, u wedge v, both grade 1 objects, we output a bivector. And like the dot product, this can be defined in terms of the geometric product as well. This time it's 1/2 uv minus vu. And hopefully you can see that when you add this to this, you can write the geometric product between two vectors, uv, as the sum of the dot product plus the wedge product. And this is actually how I motivated the whole talk of the geometric product, but it's probably more proper to view the geometric product as the underlying operation in this algebra, and the dot and wedge products as subsidiary operations. Another last note on these dot and wedge products, we also discovered that when we have two vectors which are orthogonal, that the geometric product anti-commutes. And that's readily apparent from this formula here. Let's say u and v are orthogonal. That means your dot product goes to 0, which means uv plus vu must be equal to 0. So that implies that uv is the opposite of vu. And correspondingly, we had a nice property when the wedge product goes to 0. That happens when two vectors are in the same direction. So this going to 0 implies that uv minus vu is got to be equal to 0, which implies that uv is equal to vu. The geometric product commutes when the two vectors are in the same direction. In general, if you had two arbitrary vectors, it's going to be neither of these two cases. Let me remind you of a couple important computations. Let's consider the square of e1. Remember, the square of a vector in the geometric product is the length squared. The length of e1 was 1, so e1 squares to 1. For the same reason, e2 also squares to plus 1. So that's the first type of computation I'd like you to recall. The second one is what happens when we multiply e1 and e2. Remember that the geometric product has a dot product part and a wedge product part when you multiply two vectors together. In this case, the vectors are orthogonal, so the dot product part disappears, so this is just equal to e1 wedge e2. Also remember, with the wedge product, we can flip the order of these two, just have to stick in a minus sign. So this is equal to minus e2 wedge e1. e2 wedge e1, just as the wedge product is equal to geometric product here, this wedge product is equal to the geometric product e2 e1. To summarize, we have that e1 e2 is equal to minus e2 e1. So when you switch the order of two vectors with different numbers, you've got to stick in a minus sign. And using these two computations, we can show that e1 e2 squares to minus 1. And just to review why that is, we have e1 e2 times e1 e2. We're going to switch the order of those two, sticking in the minus sign. That's going to give us minus e1 squared, e2 squared, e1 and e2 both squared to plus 1, so we're left with a minus 1. Let's now shift our focus to 3 dimensions. So we're going to set up G3 now. We're going to play a very similar game. We're going to start off with the vectors. This time we're going to have 3 vectors instead of 2 vectors. We're going to have an e1, an e2, and an e3. And now I'm going to draw these now in 3 dimensions now. So let me draw an e1 as the vector that normally points along what you call the x-axis. So that's e1. Orthogonal to that, also of length 1, just like e1 is going to be, I have e2. I'm going to draw this along the y-axis. And then finally, still orthogonal to both of those, I have my third vector pointing along the z direction, called e3. So just 3 vectors in 3 dimensions. Again, these are going to be the grade 1 objects. We have 3 of these this time. We descend to the scalars. This is going to be the same thing as before. We have 1 scalar, just numbers. We represent these as points, and these are the grade 0s. Now, to set up the next highest grade, the grade 2s, we're going to play a similar game as before. We're going to generate these objects by taking wedge products. So the first wedge product I'm going to take is e1 wedge e2, which is still going to be equal to e1 times e2. So the first bivector is going to be e1 e2. So that's the first combination of 2 vectors I'm going to take from these 3 vectors, e1 e2. So what does that look like? It's going to be e1 wedge e2. So let me attempt to draw this in down here. I have my e1, I have my e2. I'm going to draw in that parallelogram. There's e1 and e2. That's going to be that way, so I'm going to draw in the circulation symbol that way. So there's your bivector e1, e2 sitting in 3 dimensions now. So that's one possible bivector. The next possible bivector we're going to consider is wedging E2 with E3, which is also going to be equal to E2, E3. Let me draw that in. So I have my E2 pointing along the Y direction. Then I have my E3 pointing along the Z direction. Let me complete the parallelogram. Now I have E2, E3, so I'm going to draw in the circulation symbol that way, or the orientation symbol that way. And there's the bivector E2, E3, now sitting in 3 dimensions. Let me also point out that these bivectors are sitting in what you would call here the XY plane, here what you call the YZ plane. The last combination of 2 vectors I can choose from this 3 is going to be E1 and E3. Now this time I'm going to actually write E3, E1. I'm going to wedge it in the order E3, E1, even though it's arbitrary. I'm just going to do this for convenience. So let me draw that in too. So I have E3 first, pointing in the Z direction. Then I have E1. Let me complete that parallelogram. I have E3, E1, so the circulation symbol's got to be drawn like that. So there's your E3, E1 bivector sitting in 3 dimensions, and this is going to be on the XZ plane, what you normally call the XZ plane. So we see that in G3, we have 3 bivectors instead of the singular bivector in G2. So let's summarize. We have 1 scalar, 3 vectors, and 3 bivectors. From the algebraic point of view, one property that we want of this basis set for G3 is that it be closed under the geometric product. That is, if we take the product of any 2 of these elements that we have so far, we get another element that's already in this set. Now, for the most part, that's not a problem. If you consider the product of the scalar times any one of these, you'll just get that same grade back. If you consider the product of 2 vectors, for example, let's say you have E1 times E1, you get a scalar back. If you have, let's say, E1 times E2 or E1 times E3, you get a bivector. Now let's consider the other case where you have a bivector times a vector. Let's see if that's closed. Now if you multiply E1 times E1, E2, that's equal to E1 squared times E2, which is just equal to E2. We already have that. But let's consider this other case where you have E1, E2 times E3. That's something that's not on the list yet. So we have E1, E2 times E3. That's not on the list. So that's actually our last basis element in G3. E1, E2, E3. And this is going to be called, as you might expect, a trivector. And this is that last grade 3 element, because this is going to be formed by taking the wedge product of all 3 of the basis vectors at the same time, E1, wedge E2, wedge E3. Compare that to the bivectors here, where you take 2 of the 3 vectors in the basis and wedge them together. The trivector, we're wedging all 3 together. And we're actually going to have but 1 trivector in G3. So we can see we have actually all the basis elements we need. We have 1 scalar, 3 vectors, 3 bivectors, and 1 trivector. So again, as an abstract vector space, the dimension of G3 is going to be 8-dimensional because we have 8 basis elements. We're going to explore that trivector in just a moment, but I'd like to call your attention to something perhaps more important, which is that when it comes to doing calculations with the geometric product, there's nothing you really don't know how to do already. Let's review. We found that the vectors squared to 1, remember we were saying that E1 squares to 1, E2 squares to 1, for the exact same reason E3 also squares to 1. So let me write that. All these vectors squared to 1, E1 squared equals E2 squared equals E3 squared equals 1. For identical reasons that we found that E1, E2 is minus E2, E1, flipping the order of any of these 2 will result in you having to put in a minus sign. So we found before in G2 that E1, E2 is minus E2, E1. And for the exact same reasons, if you go through the algebra, E2, E3 is going to be equal to minus E3, E2. And finally, we have that third relation, that E3, E1 is going to be equal to minus E1, E3. Hopefully you're seeing conceptually what's going on. If you have two vectors and the numbers are different, you want to flip the order, you've got to stick in a minus sign, the anti-commute. And finally, just as we saw in G2, that single bivector E1, E2 squares to minus 1. The same holds for E2, E3 and E3, E1. Those two also square to minus 1. And let's review why that is, taking into account these anti-commutative relations. Let's try finding E2, E3 squared. So it's going to be equal to E2, E3 times E2, E3. We use this property here. We're going to swap this and this. We're going to get minus E2 squared times E3 squared. These both square to 1 using this up here. So we get minus 1. And you can play the same game for E3, E1. E3, E1 times E3, E1. Switch this and this. We get minus E3 squared times E1 squared. And again, that's equal to minus 1. So let's write out the full statement for the bivectors. We have that E1, E2 squared is the same as E2, E3 squared. And that's the same as E3, E1 squared. And those are all equal to minus 1. So you can see there's a nice conceptual unification going on here. What you know from G2 is going to nicely transfer over to G3. We've been squaring stuff, so let's just find out what this trivector squares to, because we already know what the squares of all the other things are. So let's consider E1, E2, E3 squared. That's equal to E1, E2, E3 times E1, E2, E3. Now, what am I going to do? I'm going to move that E3 two places to the right. So I'm going to move it here, then here. That's two swaps. So there's going to be minus minus. So I'm going to put in two minus signs, but those are going to cancel because it's an even number. I'm going to rewrite this as E1, E2. The E3 is going to get shuffled over to there. The E1, E2 are going to move over times E1, E2. Then I have E3, E3, or just E3 squared. That's equal to 1. So this is equal to E1, E2 times E1, E2, which is equal to E1, E2 squared, which we've already found is equal to minus 1. So we conclude that the square of this trivector is also minus 1. So this is yet another object in geometric algebra that squares to minus 1. Hopefully you can see you can do pretty much any computation you want to now with the geometric product. I think you already know how to do it. You may not know the significance, but you can do the computation anyway. For example, if you had 5 plus 2 times E1, E2, you want to multiply that by 2 plus E1 plus E1, E2, E3. You just follow the rules, distribute the stuff out. Remember that the vector squared to plus 1, the bivector squared to minus 1, the trivector squares to minus 1. When you want to flip the order of these two, or these, or anything in here, you've got to stick in a minus sign. So that's multiplication. Addition is as you would expect. You can combine stuff when you can. For example, if you had something like 2 E1, E2, and you wanted to add that to, let's say, 5 E1, E2, of course we can combine them in this case. You won't always be able to combine things. For example, if you had 2 E1, E2, and you had, let's say, plus 5 E3, E2. You can add these bivectors together, and there's actually a geometric interpretation for this, but you can't really do much more than this. Although you could mess around with the factor. You could factor out the E2. You could write this as 2E1 plus 5E3 multiplied on the right by E2. But sometimes there's not much more you can do. You combine when you can, and when you can't, don't worry about it. Just leave them alone. Hopefully we have some geometric understanding of what vectors and bivectors are. Remember the bivectors, those are the oriented pieces of area, pieces of abstract area. They have no particular shape, but they do have an amount of area and an orientation to them. Now let's try to understand what this E1, E2, E3 trivector is. Now I claim this is simply equal to E1 wedge E2 wedge E3. This is a claim I'll justify in future videos, but this is, hopefully it's intuitive. I form the highest grade element of G3 by wedging all three vectors together simultaneously. Now, let's try to understand what this statement is, E1, wedge E2, wedge E3. Let's draw in something that we're probably more familiar with, the E1, wedge E2 bivector. So there's E1, E2. Complete the parallelogram. Put that in. Now, let's recall what this wedge product is doing. It's forming a new geometric figure by taking one figure and extending it along the other. So you can imagine this area being developed by taking this E1 vector and sliding it in the E3 direction. So it sweeps out that area. So that's how you get a new geometric figure from the wedge product of two lower grade objects. So we're going to apply that same idea. We're going to take what we've got here, this bivector, this patch of area, and extend it in the E3 direction. So we're going to extend it in the E3 direction. So what's that going to look like? Well, I'm going to attempt to stack these patches of area on top of one another. You can imagine this as a kind of a summing of those areas, but still extending this geometric figure until we get a new geometric figure. And what's this geometric figure going to be? When I complete that extension, what I'm actually going to get is an oriented piece of volume. So I'm going to draw these in by these cubes here. Even though we should be thinking of these abstractly, this is a mathematical object which has volume information in it and has the information of the orientation of the volume, but it has no particular shape. You can imagine it as a blob, but just for convenience, I'll draw these as cubes or parallelepipeds. Just as for the bivectors, these are also abstract, but for convenience, I draw those as parallelograms. So this is the main geometric insight I'd like to carry away with these trivectors, is that they generate oriented pieces of volume. So we're going, just as we were talking about positive areas and negative areas, we can talk about positive volumes and negative volumes too. And just as when we wedge E1 and E2, the magnitude of the area that we get is 1. And that's pretty obvious because we set these up, the E1 and E2, to have length 1. So the product of those two is the enclosed area. E1, E2, and E3 all have length 1. They're all orthogonal. So the volume is just a product of all three of those. So 1 times 1 times 1. The volume enclosed is 1. So the magnitude of E1, E2, E3 is always going to be 1. And by convention, we're going to say that this thing, the E1, E2, E3, is going to be plus 1. There are many interesting things about this oriented volume element that we've just generated, but let me point out a few things just using this wedge product. So we started with E1, wedge E2, wedge E3. Let's play around with this a little bit. Remember that when I switch the order of any two, I've got to stick in a minus sign. So let me switch the order of these two. So I have minus E2, wedge E1, wedge E3. And finally, let me switch the order of these two. So I have plus E2, wedge E3, wedge E1. So this is the same thing as this. So that means that the geometric figure of this, which is this cube, this volume element here, is the same as this one. So we interpreted this one through extension of the bivector through E3 to generate this abstract volume element. So let's do the same thing with this statement here. So this is saying that the wedging of E2 and E3, which is going to be this bivector here, E2 wedge E3. Let me draw on the orientation there. E2 wedge E3 is got to get extended in the E1 direction, and that generates the same abstract volume element. So hopefully you can see that if you take this face of the cube and you extend it this way in the E1 direction, you also generate this abstract volume element. And actually, if you play around with this a little bit more, you can also show that E3, wedge E1, wedge E2 is the same as this and the same as this, which corresponds to taking this bivector on this face of the cube, which is going to have that orientation, and extending it in the E2 direction. And of course, I could always write these in a more compact fashion. I said that E1, E2, E1 wedge E2, wedge E3 is equal to E1, E2, E3. This can also be written in the more compact way, which is E2 times E3 times E1 Now this product here is a geometric product instead of the wedge product, and that's also equal to E3, E1, E2. And as I claimed before, you already know how to do quite a bit with the geometric product in terms of flipping things and putting minus signs in, so you can play around with this yourself and confirm that these are indeed equal. And again, you can swap things around as you'd like. Let's say we had E1, E2, E3, and we swap the first two vectors around. We get minus E2, E1, E3. We can negate both sides, and this is saying that E2, E1, E3 is equal to minus E1, E2, E3. So what is this trivector, E2, E1, E3? Well, it's just the opposite of that original volume element that we had. So here, we're getting some negative volume. If we're going to define these as positive volume, we're getting some negative volume here. And if you interpret this last statement, again through extension, this is saying that if you take E2, wedge E1, which is going to be this bivector here, but it's actually going to be the opposite orientation, and you extend that along the E3, you're going to actually get the opposite of what we originally generated, which was E1, E2, E3. There's one other property of the trivector that I'd like you to attempt to discover on your own. And the way to do that is just to multiply this trivector by each one of these other elements, each one of the 7 other basis elements. And what I'd like you to do is draw what you put in, draw the input object, whether it's a scalar, vector, or bivector, and also draw the thing that's coming out of that product. And see if you can discover the general relation between the input and output, and therefore what the trivector is doing when it multiplies one of these other 7 elements. Before I close out this video, there are a few pieces of jargon I'd like you to know. I've been using these names for the 4 grades. The first piece of jargon I'd like you to know is an alternate name for these trivectors. More generally, this name is used for the highest grade element in the geometric algebra, and that's going to be the pseudoscalar. So in G3, the trivectors are the pseudoscalars. And we're going to develop that concept a bit further, but just know that these pseudoscalars are going to be the highest grade elements of the geometric algebra. In the case of G3, that's the trivector. The next highest grade, in this case, those are the bivectors. Those are also called pseudovectors. And again, we're going to develop these concepts in more generality. In this case, G3, the pseudovectors are these 3 bivectors. In physics, these are sometimes also called by yet another name. These are axial vectors. So the pseudo prefix is telling me that they're not quite vectors, they're false vectors. But as I said, we're going to develop that concept a bit further in future videos. And the vectors, there's no other piece of jargon. Actually, there is one. Again, in physics, in contrast to these axial vectors, sometimes people call these true vectors, polar vectors. So just a few pieces of jargon I'd like you to know. The most important ones are the pseudoscalar for this oriented volume element in G3, and the pseudovectors for these 3 types of bivector we're going to be working with. As I said earlier, if I've been at all successful in this video series, I don't think this video really added too much more to your knowledge. By the introduction of one more vector, moving from G2 to G3, we add in 2 more bivectors, 2 more pseudovectors, and then we add in the pseudoscalar, the grade 3 element, which was that directed volume element. So those are the main concepts, and I think this is going to be a good bit of fun because there's a lot of cool physics we're going to be able to do, especially with gyroscopic precession, which is a video I'm pretty excited to make. After all, Vsauce did some rotation stuff, so I've got to steal his idea. So hopefully stay tuned for more videos on geometric algebra, and as always, leave your angry comments and subscribe to the channel if you enjoyed the content, and I thank you for watching.